Welcome to the second part of lesson 18D&E. In the first part of the lesson, we looked at what a bell curve does and how we can come up with normal distribution curve for different data sets that has sort of this mound-shaped symmetrical distribution. And all bell curves can actually be mapped onto or compared to what we call a standard normal distribution, Z, that has a mean of 0 and a standard deviation of 1. We looked at if we know a certain position on that bell curve, we can find the probability of getting that value less than that value or greater than that value, or we can also find the probability of something falling between two different positions, so to speak, on the bell curve. So now in this section of the lesson, we're going to look at something called the inverse normal distribution. So instead of looking for the probability is given to us, and we want to find out where can we locate, that position that gives us that probability, and what does that mean in the context of a problem, right? So the question we're trying to answer really is the probability of Z less than or equal to question mark equals to P. We will be using the graphing calculator extensively, and because between the time of when this lesson was made and how calculator OS has been updated, there are more options for you on the TI-84 calculator, 83 to do these math. So for the sake of simplicity for now, all the calculator instructions will be based on how this lesson goes, because it works for most of the models that different students have in our class. If you want to experiment with the more extensive list of options, so to speak, you can request it, or if I have time, I will make another video to experiment with the different options, the newer options, that will probably make your calculations more efficient if you have a more, so to speak, advanced calculator. Okay. So in general, to calculate inverse normal distribution using your TI, you need to invoke the second function vars to go into the distribution menu again. The function that you want to use is the inverse normal, so usually it's the third one, inv normal, and then you punch in the probability value. Okay, so we'll look at this using specific examples. So example 4, find k such that p of z is less than k is equal to 0.975. So notice how this is a z value, so that means we are referring to the standard normal distribution with a mean of 0 and a standard deviation of 1. All right, so less than means we're to the left of this value, the probability is 0.975, which means that we're pretty far off to the right side under the curve. So to find the associated k value, the z-score really, is to do second vars, and then inverse normal, so 3, punch in 0.975, mu is 0, sigma is 1. If your calculator has a tail option for left, center, right, keep it as left. Okay, don't touch that yet. So keep it left and then paste and then enter. If you use an older calculator, you'll be entering inverse normal, bracket 0.975, close bracket, enter. It should give you 1.9599, so round it to 1.96. Okay, does that make sense? I think so, because we are approximately 1.96, very close to 2 standard deviations above the mean. In part B, we're going to look for probability where we're going to have this data point that gives us a probability that anything to the right, greater than this number, is 0.452. Once again, we're sticking to the traditional standard calculator functions. So what the traditional calculator does is it doesn't allow it to calculate anything greater than, right? Remember from the binomial, same idea. So we only can calculate anything to the left of the k value. So we need to kind of tweak it slightly and say, well, what's the equivalent probability then? It will be 1 minus 0.452. That gives us 0.548. Okay, So to find k now, we can do inverse normal. So second vars, 3. The area is 0.548. Mu is 0, sigma is 1, tail is on the left side, and you paste it. And this is 0.121. So we're just slightly above the mean, right? A z-score of 0.121 is slightly above the z-score of 0 at the mean. All right. Now, maybe it's time to look at the tail option on some of your calculators. I am using a TI-84 plus CE. So if I go back to the inverse normal function, if I type in area 0.452, the mean is 0, sigma is 1, and the tail, well, because the tail we're looking at is on the right side of k, you will have to select right. And then paste and then enter. It should also give you 0.1206. Okay, so that's what the tail part does. If your calculator doesn't allow that, you're not disadvantaged at all. Okay, you can get the same result following the steps that you need. Okay, so that was using the standard normal distribution of Z. Okay, so in example 5, we have a new question that is not on a standard normal distribution, but instead it's a normal distribution with a mean of 50. And the second entry here, 9.61, it really stands for the variance. So you need to tweak it, take the square root of that number to as the standard deviation. Okay, so don't forget that. And then we're looking for k such that p of z less than k is equal to 85%. So anything up to k takes up 85%, of the area under the normal distribution curve. So using the most basic form of inverse normal, assuming that we're still dealing with z, so it's the mean is 0, the standard deviation is 1, you can quickly, on the calculator, go to second vars. Inverse normal area is 0.85, sorry. Right, and then the left tail is what we're looking for the less than area. And it will give you 1.364 ... which is about 1.04 as the position, right? 1.04 standard deviations to the right of the mean. Now, translating this onto our particular normal distribution, the mean is 50 now. A z-score of 1.04, what does that mean with respect to the numbers here? Well, you're going to substitute 1.04 into the z-score equation, and then it's equal to the data point k minus 50, the mean, divided by the standard deviation, so which is the square root of 9.61, correct? And then that will give you k equals to 53.22. Now for the more updated calculators, if you go to second function vars, inverse normal, when you punch in area 0.85, if you want to do this directly, you can set mu to be 50 as the mean, and then make sure you type the square root of 9.61 as the sigma, left tail, and it should give you the same result. So also one thing to note, when you go in to type in the square root, make sure you close the bracket, close the ending brackets after you type in 9.61, okay? Otherwise, the syntax will be incorrect, all right? You should get the same result though. Moving on. So IQ scores, example 6. IQ scores are normally distributed with a mean of 100 and a variance of 15 squares. Sorry about the typesetting here. So we can let x to represent IQ scores, and then x belongs to a normal distribution with a mean of 100 and a variance of 15 squares. So that means the standard deviation is 15. So what approximate percentage of the population will have an IQ between 85 and 125? So in probability notation looks like this. Using the graphing calculator, we're looking for probability, so that means we're doing a normal CDF. So we can follow this command. The lower bound is 85, upper bound is 125, mean is 100, and then standard deviation is 15. And then calculate that, 79.4%. If you use the Z-score method, if you prefer, you can convert each one of these IQ scores, 85 and 125, into the respective Z-scores using normal CDF without changing the mean and the standard deviation. So you're sticking to 0 and 1 as your mean, mu and sigma. You will also get the same answer. Okay, part B. What percent will have an IQ greater than 85? So now the notation would be, we're looking for probability of x greater than 85. This means that we need to use the normal CDF function. So if you pull out your calculator, second function vars, number 2 normal CDF, we can start with a lower bound of 85 and upper bound of a big number, like 1,000 or more zeros, if you like. The mean is 100, standard deviation is 15. Okay, and then if you calculate that, it's 0.84. 134, so round it to about 84.1%. Okay, that makes sense because an IQ score of 85 is lower than the mean of 100, so you have more than 50% of the population for sure. Next, what IQ corresponds to the 84th percentile? Well, the 84th percentile is the cumulative probability. You can think of it that way, right? So 84% from the low end. So you stop at this point. So this reminds us of what we just learned earlier in this part of the video, which is the inverse normal function. So the most direct way to do this is to do second function vars, 3 for inverse normal. Type in 0.84 as the area. If you stick to the standard normal distribution, so the mean is 0, sigma is 1, left tail, you will end up with the k value or the z-score as being 0.9945. And then you plug it into the z-score formula, rearrange it, and then, oh, whoops, this didn't show up, but you're going to get 115 as the IQ score. If your calculator can allow you or will allow you to enter the actual mean of 100 and the standard deviation of 15, you should be able to get this 114.9 or 115 right away. Okay. And then D, in a class of 30 people, how many will have IQ less than 70 or greater than 135? So an IQ of 70 is on the low end, right? And then the IQ greater than 135 will be on the high end. Well, instead of adding the two tails on the diagram, what we could do is we can take the entire 100% of the population and then subtract the in-between area. So we can do this in one shot. So here's the setup. Right, adding the two tails, the greater than less than 70 or greater than 135 is equivalent to 1 minus the in between 70 to 135. If I use second function vars, normal CDF with a low bound of 70, a high bound of 135, mean of 100, and standard deviation of 15, it is 0.9674. Subtract that from 1. This is the percentage of the population that will have these scores, right, between 70 and 135. Now, we're looking for the how many people, so we just multiply this by 30, right, as the class size, and then you get 9.78 people. So roughly 10 people out of 30, a third of them, will have this IQ score range. So we have looked at how we can find probability and solve probability problems using the bell curve. Now is your turn to do some practice.